All right, we are live. So today I actually want to follow up on the solutions that I gave you for exam 3, and particularly problem number 4, because I actually did not complete problem number 4. I missed one of the last parts and maybe gave you the wrong impression. So let's kind of go back through the notes. So what I talked about is we have a cylindrical tank, and we're basically looking at a level control problem. If you kind of go through the problem, you can calculate the diameter as a function of the height, get the area as a function of the height, and then basically we come down to a model where we have dH dt is 1 over the area, F in minus F out. And F out's our manipulated variable, F in is our disturbance variable, and H is our output or controlled variable. We can basically, let me kind of slide this up over here, kind of getting a little complicated. And basically we can linearize it, and what we get is basically the transfer function that h prime is 4 over 49 pi s, f in prime minus f out. And as I mentioned, this is an integrating process because we don't have a time constant here. Actually, we have a pole solely at 0. So there's no kind of, the notion of a time constant because basically it's at 0. All right. So what we did before is we had two transfer functions. Actually, the g and the d are the same. One has a minus sign, one has a positive sign. And then we can use the formula for calculating a controller where we invert the transfer function g, and then we take 1 over tau cs, where tau c is our desired closed loop time constant. And in this problem, we're told that we want it to be 5. So this becomes 1 over 5s times minus 49 pi over 4 times s. And basically, you get back a p controller, which is minus 49 over 20 pi. And this is just a number, right? So I think it's like 0.02 or something. Or wait, actually, no. I got it backwards. So that's like 2. So around like 7 would be the number, or minus 7, because we got the minus sign. So that is simply a proportional controller. And the other way to think about it is we can just write our Kc as minus 49 pi over 20. And so then I asked, is there 0 offset? And I should emphasize this is for the set point. Right? There's the set point. So what I didn't talk about is disturbance, which I'll get to in a second. So regarding the set point, the answer is yes by design. So we get GC all over 1 plus GC is 1 over 5s plus 1, right? And in general, when you have an integrating process, and I mentioned there's a proportional controller, right? So let me step back. I'm getting ahead of myself. So when we have 1 over 5s plus 1, our gain is 1, right? So that means when we sketch the response, right, we're going to have our plot, and then we're going to go to 1, and that's our 1, right? And so basically we had a unit increase in the set point, a unit step increase in the set point, and our response, y, is going to give a first order response to 1. So we're going to match the output and the input match each other because the gain is 1. And in general, for an integrating process and a proportional controller, if you have GC over 1 plus GC, basically you get KKC over S plus KKC, or the other way you can rearrange it is 1 over S over KKC plus 1, right? And basically, again, if we look at this, our gain is 1. So we're going to always be offset free with proportional control. But that's offset free in the case of a set point response. So this is kind of the new part. And that's basically, what about the disturbance response? And in this case, actually, we're not going to be offset free. So this is kind of one of the unique things about integrating processes is that we can get set point control, but if we get hit by a disturbance, it kind of breaks down. So here our D is 4 over 49 pi, 1 over S, right? And if I look at 1 over 1 plus GC, we know that's just 5S over 5S plus 1. That's almost by design. And so when we take D all over 1 plus GC, we're going to get the 4 over 49 pi times 1 over S. That's the D. And then our 1 over 1 plus GC is 5S over 5S plus 1. Now, normally you would think that when we have an S in the numerator, that's going to get rid of the disturbance response, or going to give you offset-free disturbance response, but we're going to have these two S's cancel out. So this S and this S, they're going to cancel out. And basically, this is reduced down to 20 over 49 pi, 1 over 5s plus 1. And so the key here is that the gain, right, we actually have a gain here. And that means when we do the disturbance response, right, we're going to have the first order response because this is first order. We have a time constant of 5 and a gain of 20 over 49 pi. And so we're going to have that first order response. The final value is going to be 20 over 49 pi. And then here's kind of our 2/3 response at 5. But the key thing is we're not going to 0. So it's not like we're going up and coming back down, which is a normal disturbance response. Here we actually have offset. And the reason we have offset is because we don't have an integrator in the system. Now it's kind of weird because we kind of do have an integrator because the system is an integrator. But in the case of the disturbance, we kind of lose that. And the reason why is because, well, basically the reason why is the math doesn't work out. And you kind of see that you don't get the offset-free control. So really, if you want to get offset-free, we'd actually have to have PI control for this example. But this is one of the weird cases where you can have offset-free control for set point responses, but you can have offset when you have disturbance responses. So these level control problems are a little bit different than kind of our standard problem. This is a little bit of a trick question, but also illustrating kind of a key point. And so in this case, designing your system for a set point response, which is the normal thing we're going to do and is what I expect you to do on the exams, isn't always the ideal scenario. Sometimes you would actually have to design the controller based on the disturbance response. And I kind of sketched out previously how you could use that same formula to actually do a model-based design for disturbance rejection, right? You could specify that, what we could do is we could do something like D all over 1 plus GC, and then we could force this to be equal like, say tau C S all over tau C S plus 1. And then we could solve for C, and that would make sure we get rid of our disturbance rejection because we have an S in the numerator. But when we did this for P control, right, using this formula, which is basically we're saying that GC 1 plus GC is equal to 1 over tau C S plus 1. And basically here, when we come back to this equation, what we're doing is we're actually just solving for C here, right? Because our G is known, our tau C is given, and then we can actually solve for C. Even though this design gives us offset-free control because the gain is 1 by design, it doesn't give us offset-free control in the case of the disturbance part because, as you see with the math, we basically have a gain in the system, right? And we have a first-order response. So that's kind of the solution of the problem. Hopefully my explanation is clear. But it's just to illustrate that, not all the time does the disturbance response nicely simplify out. And, someone asked me whether you can jump, right, immediately to the solution, right? So like here in this equation, basically, I jumped right to it because I already knew the math. I don't expect you guys to rederive this every time, but make sure you understand when it works and when it doesn't work. And sometimes you got to look at the math to see if you're going to get offset-free control or not. Anyway, hope that was informative. A little bit rambling. I apologize about it. It's kind of a complicated problem. This is definitely a trick problem. I would classify as one of the more challenging problems I've ever asked on an exam. But hopefully the solution is clear. If you have questions, put them in the comment section or put them on Piazza. I'll do my best to answer them. Anyway, stay safe, guys. Have a great weekend.